Well, thank you He-Man for that excellent intro. We do indeed have the power. Or do we? Watch on to find out. I've been accumulating a lot of USB-C devices. It started off with a mini hot plate, and now I've also got a TS80P soldering iron. Both of these devices have a USB-C input and take advantage of the various quick charge and power delivery options to get the most out of their power supplies. I have got this really nice gallium arsenide 65 watt USB-C power supply, but it would be nice to be a bit more portable, particularly with the soldering iron. Now I could go out and buy a power bank. That would be the most sensible thing to do. But I've had these 10,000 mAh lithium cells lying around for a year now, so I thought I might as well buy a charging board and go with them and make a DIY version. Let's see if this actually makes any sense at all. The board I'm using states that the batteries need to be able to supply up to 10 amps, so I thought we should probably check that first. Wiring up the battery to my electrical load doesn't give a very promising start. We only get 3 amps before the battery's cut out. Even with 2 of the batteries in parallel, we'll only be able to get 6 amps in total, nowhere near enough. My initial suspicion was that this was due to the battery protection boards being a bit too protective. Fortunately, along with the 10 amp requirement, we also have these instructions telling us to remove any battery protection as it's all built into the board. It's pretty easy to do this, we just need to unwrap some of the Kapton tape and then the battery protection port can just be desoldered. It comes off surprisingly easily, which does make me wonder how well it was attached in the first place. Removing the battery protection board also lets me solder on some much thicker and more flexible wires. The ones that came with the battery seem to be pretty thin and stiff. Wrapping this back up with Kapton tape, it's the perfect crime. It looks perfect, like it was made to be like this. With the battery protection board removed, we can easily get up to 10 amps from a single battery. We can even go much higher if we wanted to, but 10 is plenty. With 2 batteries in parallel, we'd get a whopping 20 amps. Connecting the batteries to the board is pretty simple. You can safely wire up lithium cells in parallel provided they have the same capacity. They will just self-balance during charging and discharging. However, I did make sure before connecting them that I discharged them to about the same voltage, so there won't be any big current surges between them. The control board does have a resistor to set the battery capacity. Fortunately, my board is already configured for 20,000 mAh, so there's nothing for me to do. With it all wired up, it charges nicely. The control board is pretty nice and it takes advantage of the various fast charging options to take the input power up to 21 watts and speed up charging. If we measure the voltage across the battery terminals, we can see that it is definitely charging them up. The voltage is increasing. With it fully charged, we can test the real-world capacity. But first, a quick word from our sponsors, PCBWay. PCBWay have been sponsoring the channel for a while, and we've had a bunch of PCBs manufactured by them over the past few years. They also offer 3D printing, CNC machining, and much more. Check out a link to them in the description. They are really great. So, I've hooked up my electronic load. The maximum current I can pull by default is limited to 3 amps. Trying to go above that triggers the board to shut down. However, I can use my USB power monitor to switch into Huawei's supercharged protocol, which gives us 5 amps output. Not bad at all. Unfortunately, after the discharge is complete, we only seem to have measured 12,000 mAh. That's quite a bit lower than I expected, but it could be just the power monitor is affecting the results and taking away some of the amps. So, I've recharged the batteries and we'll try again. As I've left out the USB power monitor, we won't be able to trigger any of the fast charge modes, which means we're limited to the default 2 amps output at 5 volts. Assuming we do have 20 amp hours at our disposal, this should take almost 10 hours to discharge. Unfortunately, this has produced some very similar results, just under 14,000 mAh over 7 hours. Measuring the voltage of the batteries, it looks like there's still some juice left in them. We can also check that the battery protection has not cut in by measuring the voltage here, and it looks fine. So I've hooked the batteries up to the electronic load directly and discharged them, and sadly it actually looks like there's not much juice in them at all after all. Maybe the batteries are not 10,000 mAh. There is quite a suspicious review on a similar listing on AliExpress for the same batteries. So I'm now doing what I should have done in the first place. I've fully charged the batteries and I'm measuring what the actual capacity is. So let's kick it off for the first battery. If it's 10,000 mAh, then at 3 amps it should take around 3 hours to discharge. And here's the result for the first battery. It's bang on the money, 10,099 mAh. So let's check the second battery. We'll reset the stats and kick off the test again. I'm starting to suspect that it's going to come in at around 10,000 mAh as well. And the results are in, it's 10,039 mAh. So it turns out the batteries I got from AliExpress are actually really good. I owe them an apology. So we've got 20,000 mAh capacity, but we're only getting 14,000 mAh out. Does that mean our power bank is only 70% efficient? If true, that would be really rubbish, especially as the datasheet claims up to 96% efficiency on the boost output. Well, it turns out that, as always, things aren't that simple. When looking at a power bank efficiency, we should be looking at the energy and not the amp hours. I've put a link to a great website that explains all of this in detail in the description. Our two batteries give us 20 amp hours, and they have a nominal voltage of 3.7 volts. That gives us 74 watt hours of stored energy. Eagle-eyed viewers will have seen that as well as the milliamp hour value on our discharge monitor, we also got the watt hours. We measured 69 watt hours of energy on the output. This means our efficiency is actually over 93%. That's a pretty good result. Our power bank is actually very good. Now, this shouldn't really be too surprising. The actual control board is pretty amazing. There's nothing really on it at all. All the heavy lifting is taken care of by this one chip, the SW6206, so you would really have to mess things up to make it not work properly. The IC supports a completely bonkers number of output options. Absolutely amazing. These other ICs are just MOSFETs for controlling the outputs, and this single chip battery protection IC, the XB8089A, is the reason we can remove all the protection from our batteries. Let's test out some of the output options using my USB power monitor. On the USB-C output we get these options, and on the USB-A outputs we get these options. I did have to apply a bit of load to the power bank or it shut off automatically. You can put it into a constant output mode by holding the button, but then the power delivery options don't seem to work. This might get annoying after a while. Trying out the TS-ATP soldering iron, it works okay. On the USB-C output it only uses 9 volts, which is okay, but it's not fantastic. But on the USB-A outputs we get up to 12 volts, which is the maximum voltage the TS-ATP can run at, so that will work nicely. The mini hot plate is not as promising. With my gallium arsenide power supply, it will draw 20 volts and heats up really quickly. But with my power bank, it will only draw 12 volts, so it heats up quite slowly. Now of course, this is not that surprising. It matches what we saw with the USB tester, and it also matches the spec of the control board. It does only go up to 12 volts on the output. So on the question of DIY versus buy, was it really worth it? Including shipping, the cost for the batteries was around £17, and the charge control board was around £4 to £5, so our total cost was around £22. This comes out slightly cheaper than some of the commercial versions on Amazon, so I think it's a bit of a toss-up. It's a fun project, but you would probably be better off just buying one. There are some 65 watt power banks available that would be able to run the mini hot plate at full whack. They are slightly more expensive, but maybe an extra £10 to £20 or so would be worth it. I haven't found any 65 watt bare PCB control boards, so for now the DIY route is out of the question. Let me know what you think in the comments.